first speaker is Bart Anderson from the University of Sydney. The title is Inverse Optics, actually ill-posed. That's very stimulating, the topics. I hope the very hot debate about that. So please.
There's an on button, all right. Well, I had to make a decision about how to parse the two talks that I was asked to give. So I thought I'd try to do something a little bit more of a theoretical overview and also something provocative. I thought this was going to be more of a discussion type of workshop, so hopefully I'll at least provoke some comments, if nothing else. But this is something I've been concerned with for a very long time, and I think that most people who ever have thought about this question or know what they mean by, or think they know what they mean by inverse optics would usually answer yes to that question. But I'd actually like to make the argument, and I'm going to try to convince you that if you answered yes to that question, you either believe in evolutionary magic, or probably you're using the term inverse optics in too narrow a sense, right? And probably both, right? So what I'm going to try to do is to save inverse optics in some sense, and try to give you a sense for why I think there's an inherent contradiction to embrace that particular view. Now, part of my motivation is I've read a lot of papers with this kind of introduction to why people are not trying to solve inverse optics or do some type of inverse optics. And the basic claim is that inverse optics is either too hard or impossible for it to be what the visual system does. It's just no one can figure out how to do the inverse, so it can't be doing that. Therefore, vision must be doing something else. And the issue in debates basically involve trying to figure out what that something else is. And it was nice for people to invite me here because, you know, I got into this field by starting a debate on what that thing is or what it isn't, right? And it's nice for them not to hold a grudge against me, right? All right, so let's look at where this idea comes from. And basically, we have this notion that we have we know what optics is. We have there's a world that's out there that has some set of unknown properties or a set of properties that are specified by physics, and through optics, the transformations of the way light interacts with surfaces and materials, we get images. And that's relatively the easy part, as Ted Adelson used to like to say. That's why the computer graphics conferences have gotten more and more money, and whereas we're still struggling to figure out the other side of it. They've gotten very good at figuring out the forward problem. We saw some of that progress this morning. But this other problem is that we have this notion that going from the world to image is a destructive process, and the most obvious ones that we usually think about are the collapsing of depth, the third dimension. And therefore, to go from the image, from the input to the perceived world, we have to somehow construct that mapping. And that's what we typically refer to as inverse optics, or in the sense of what we're trying to do is to undo whatever that destructive transformation was, right? And in this context, what vision becomes is a collection of ill-posed recovery or estimation problems. We see this a lot in things like color constancy. How do we recover the color of a surface? How do we cover the shape of the surface? How do we cover the lightness of a surface? So you have this notion that what the visual system evolved to do is to estimate particular physical dimensions of the world. And the presumption is that there's insufficient information encoded into the input to be decoded uniquely into a unique set of world states, right? So what therefore follows is that some inferential machinery must therefore be built in the visual system to allow the visual system to do this decoding, because the input is inherently ambiguous. And I think this is where the crux of the issue lies. The other thing I've become somewhat famous for, is my stance or questions of the depth, conceptual depth involved in Bayes' theorem. But this is the modern version of what we think of as the inferential process, or how we can at least formalize this inferential process. And I like to call this the secret decoder ring, right? Somehow, if we have an ambiguous input, then we have to have some kind of decoding rules that can tell us how to actually go from the ambiguous input into the output. And it takes a form such as this. Everyone knows we can ignore the denominator because we don't care about the normalization scaling in the full Bayes theorem. So we have what we're trying to get is the probability of a given world given an image. And what we need to do to compute that probability is we need to know something about what the probabilities of the different world states are and what the likelihoods of a given image given those world states, right? And so these two things, the prior contains the list of the world states, right? So in the world of material perception, these could be things like object shapes, reflectances, materials, and illumination. And the likelihood relates world states to images. So the interactions between light sources, shapes, materials, affects the perspective, projection, and viewpoint. So this is all the kind of information that we need to do these inferences in a Bayesian way. The question that I want to raise, and the one that's always troubled me that we very often ignore, is that if this information can't be derived from the input, how could it ever get into our heads? And I think this is the deep fundamental question that nobody asks about to say, well, the input is ambiguous, therefore we need something that's going to do the decoding. But how does it get in there if we can't get it in some sense from the input? And I think this is the logical paradox that I think is the real problem for any attempt to try to solve the problem in this type of way. So here's the basic evolutionary model, right? Basically what we have is the evolutionary explanation really is little more than just a list of ingredients. And we have basically a sense of a very long time. We have some randomness, and then we got this something which selects something. Then just wait long enough, we get this decoding device, right? That's basically the whole thing. It's just a set of ingredients. And this is my version of this theory. I don't know if people have seen this cartoon. This is one of my favorite cartoons. You can't read that, and you see a picture of a proof, and in the middle it says, then a miracle occurs. And he's being, maybe you should be a little bit more explicit in this step, right? And I think that this is basically the problem, is that we just assume that somehow we need this stuff, but we don't have any sense for how this stuff could ever get in our heads. And so here's a core claim I'm going to make. I don't have time to kind of try to flesh out the full arguments of everything or do this in any more than trying to make a point, is that the presumed intractability of inverse optics rests on the premise that there isn't sufficient information, right? So this is where we started from. But this intractability and the way we usually demonstrate the fact that you can't do this inverse is usually done for isolated sources of information. We do size constancy, we get the same different retinal sizes for objects of different world sizes, stripped of all the other information that could be brought to bear to solve that problem, right? But obviously in an environmental context, we had all of that information, all the correlations between things to actually help us solve this, right? And here's the basic claim that I want to make, is that the capacity to differentiate between distant sources of optical structure, which is fundamental to material perception, implies that there must be information available to make such discriminations, right? There has to be something there that supports our capabilities. That's a claim, right? That's basically going to be my main argument. And I think that without that claim that you embrace magic, right? The evolution of perceptual abilities was therefore a process where we should think of it as organisms were selected on the ability to use available information that reliably distinguishes different environmental sources. So there's different set of causal variables in the world that structure the images. And we can separate out illumination to some extent. We can separate and shape out to some extent. Our capacity to do that has to be based on information that's available, right? And any account that requires having a list of possible answers, like a list of world states and likelihoods, begs the very question that evolution and learning is supposed to solve. The problem of resolving ambiguity is, in fact, not solved, it's merely displaced, right? And this is kind of hearkening on to, I think, some of the things that Ted said, but I'd like to push it a little bit harder. I'd like to actually say that it's a requirement that is, in some sense, whatever our capacities are, they can be learned from the input. Or there has to be some signals with which natural selection can pick out the animals that use those signals in reliable ways, right? So there's basically two different sources of evolutionary magic, mutation and natural selection. The list of possible answers, if it can't be derived from the input, must be generated by mutations, right? But my way of thinking about this is that this is exactly like you just somehow the world's knowledge will arise in your head is not unlike the classic example of waiting for one of Shakespeare's plays to arise from the random keyboard strikes of a monkey hitting a typewriter, right? It's not impossible that it could have happened, but it's just so extraordinarily improbable that it would happen that it doesn't seem like a viable theory on which to base a theory of perception, right? So the problem is unchanged if such changes are the product of epigenetic changes. When they say, what about epigenetics? Maybe we can do it this way. But that also, or learning, because learning and epigenetics, all this also requires some signal that discriminates some class of events from another class of events. So basically what I'm trying to do is dispel evolutionary magic, saying that there has to be sufficient information available to support the classic distinctions that we actually make. Now, we're not actually necessarily trying to explain how it is we recover a specific parameter of the world. We're trying to understand how it is we recover what we do recover about the world. And that's a very different notion, right? And you can't just start with what a physics problem tells you is the input and then say what would be the best way to try to get that out. We need to try to figure out what are the class of distinctions, perceptual classes, categories, discriminations that we can make, and what's the informational basis of that, right? And notice also, and this is a big thing about the pragmatics of evolution, these distinctions don't have to be right in the sense that they don't map onto a particular physical dimension in the way that we think they should. They simply have to be based on some distinctions that can be extracted based on that input. Don't worry, I'll show pictures soon. I mean, this is just the intro. This is just all set up. This is the foreplay for trying to show you how I've come to think. And this is kind of the crux for me. I've been spending a lot of my life studying lightness in recent times. I actually think I've wasted some of my time doing that. I'm going to tell you some of the time I've wasted on this. But because I don't think it's necessarily particularly important to know something like the absolute lightness of the surface. But I think that what is important, and something that I'm very intrigued with and I think that we are extremely good at doing, is qualitative or class distinctions, separating the input into different causal sources of image structure. These are typically things we call intrinsic images. We can tell if certain classes of structure in the image are caused by an illumination change or by a reflectance change or by a change in surface orientation. We're really good at accounting for the different causal sources of structure. But the other aspect of this, the one that psychophysics has spent most of its time obsessing over, is the scaling of a particular dimension, like quantitative amount. So how much lightness, how much lighter, how much darker, right? And these scaling magnitudes is quite an interesting thing, is that this is actually the historical meaning of psychophysics. It was the thing that made psychology a science, right? What are the mathematical constraints? So can we express our changes in sensation in the same way that physicists can express changes in quantities? But I actually think that many of the quantitative distinctions that we make aren't particularly relevant. Lightness will be one of my examples. Does it really matter if we know if it's light gray or dark gray? Right? And I think that some of the reasons that it doesn't matter is shown up in perception, which I'll try to point that out to you. There's also, although it's a historical focus, it's not even clear what it would mean to get it right. Why, for example, is in lightness perception, 18% reflectance considered mid-gray, when it can span a scale of up to 90% reflectance, right? So what would be the right answer? Why is it's not even clear that question makes sense. All right, so what's the basics? How are we going to do this? Well, why this seems so hard? Well, look, inverse optics seems so hard because you've got this three-way interaction, right? The interaction between the illumination field, 3D shape, and the reflectance and transmittance properties of surface and materials. You've got too many degrees of freedom. How do you extract them out? Now, when we think about this from a particular image or a particular restricted stimulus space, this seems analytically complex. There's nonetheless strong physical constraints on how these different variables interact. This idea harkens back to Marr, by the way. And I objected to it back in the day when I was reading Marr, but I think he was actually fundamentally right and onto something with thinking about physical constraints. But the point that I want to make, or the claim I want to make, is that many of these constraints, and I'll talk more about this at APZV, that if you know something about depth, if you know something about the 3D structure of the scene, a lot of the other information falls out of that, right? I think that, for example, we still spend way too much time trying to get too much out of the raw unprocessed images. And that's my last point, right? One of the main things that how I got into this field was that many of the constraints that exist that will disambiguate the stimuli only occur at higher levels of representation where 3D shape is made explicit. And if we try to do all of this just based on the raw image, I think that we're not going to get very far. And I think this is actually one of the big issues and one of the barriers to progress. Okay. And the main thing that I'm going to now take you through a series of examples is that these physical or generative constraints induce photogeometric constraints in the input. Now I'm going to try to make this clear to you, but basically what I'm going to claim is that our task is to try to identify what those constraints are and how it is that they provide the informational basis for the distinctions that we make. And that's a lot of words, right? It's a lot of theory. Let's see what I'm actually doing with that. So let's go through some examples. And I'm going to take you through a little bit of his history and some recent work as well. Let's start with example 1, transparency. This is a little bit how I got into some of these problems. So basically, this is a field that it was one of the first places that physical constraints was taken very seriously as both a model of the generative process, but also a perceptual model. So I presume many of you, if not all of you, know something about Metelli's model of transparency. You had this, back in the day, in order to generate this, you had this rotating disk with a missing sector, and if you spin it really fast, you get this perceptive transparency. And you could write the regions where they were combined, the transparent layer and the underlying layer at P and Q, as just a simple sum of the weights of the underlying surface and the transmittance of the open size alpha, the proportion of the sector that is missing from this episcotisser. And you can write down these physical constraints. Okay, notice that these constraints, however, have no geometric content to them. Right? All they are is photometric constraints. They're just saying something about how the intensities are related to each other. Nothing about the geometry about what's invoked in them. But for transparency, we know that we need both. Right? You have to have the geometric constraints and the photometric constraints of the right kind in order to elicit transparency. You violate either one of them, it doesn't work. Right? So we know that these photometric constraints actually can provide some diagnostic information about the transparent surfaces. Preservations of contrast polarity, but reductions in the magnitude of contrast polarity can become signatures of the presence of transparency. And the magnitudes of that change tells you something about the opacity of the transparent surface. So if you go from the top to the bottom, you can see that it looks like it's getting more and more opaque, right? And they all look transparent. And we can exploit these constraints. So this is the first game that I played when I was getting into transparency. We can exploit these constraints to induce transparency. I start with textures that are identical like this, and I flip the contrast polarity of the surround here, flip relative to the one on top, and I provide the continuity of the textures, and I can induce such illusions as this, right? Where you see like white chess pieces through black fog, and you see black chess pieces through white fog, all due to the way that the contrast is varying along the contours and the continuity of the texture that cuts across those contours. Right? So these are diagnostic cues about the presence of transparent surfaces. However, in some work I did with Manish Singh, now nearly a little over 12 years ago, basically found a very systematic thing which Metelli noticed, is that people misscale the opacity of the filters. They conflate the actual color of the filter with its opacity. So if I paint an episcotisser white versus black, the white one looks more opaque than the black one, even if the sector, the actual physical transmittance, is the same. What you can see is that what people are actually using, and this was because we used sine wave gratings as our stimuli, we can plot this in terms of Michelson contrast, is that basically what people are doing is just looking at the relative Michelson contrast to come up with an estimate of the opacity. So from a physical point of view, this is a scaling failure, right? This is physically getting the answer wrong. You're not getting the true transmittance of the surface. But who cares, right? What's the evolutionary cost about that? Knowing what the cause of the change is provided in the information, and it's probably of much more significance than this kind of scaling error. Second example, lightness perception. Right? So this one is some recent work. And this is actually kind of how I've gotten into some of these issues, which is that I spent a lot of time trying to figure out how it is we see the lightness of things. And at some point, I step back and ask, why am I studying this problem? Right? Here's the typical generative model we have. If we have a Lambertian surface, so something that we can, the important thing is that we can characterize its reflectance with a single number. So we can talk about it having a lightness, right? By that fact, we can now say something about, we say, what's the lightness of a surface? In order for that question to even mean anything, that the term lightness has to be a singular quantity. So we assume a Lambertian surface. But the problem is that in most cases, if we look locally at the information in the image, we notice that what we get in the images is a luminance. But that luminance is, in fact, a product of reflectance and illumination. And that seems hopelessly intractable, right? How can you possibly figure out one from the other? It seems completely ambiguous, right? However, one of the things that we are identifiably very good at is identifying which portions of the scene actually are generated by changes in lightness versus changes in illumination. So, for example, if you look at this house over here, you can tell that the top part of the roof here is actually painted a different color, but you can tell that this edge here is actually just a change in surface pose. You can also tell what are cast shadows in this image. You can account for the structure of the image. The same thing with the cast shadows over here on the right. We can tell that they're actually shadows and they're change in illumination. But if you actually try to get people to make lightness judgments of those isolated regions, I promise you, you always get something where the estimate is going to be a trade-off between what it's just white and the actual brightness of that region. And people have exploited this. Many people have made careers out of studying this ambiguity and trying to figure out how to solve it. So Alan Gilchrist, for example, had done some studies with domes. These are fantastic phenomena if you haven't seen them. They're actually quite stunning to look at. You get in these domes, he lowers these domes on your head, you open your eyes, he just asks you what you see. And it's a world with a single edge in it. And so if you look at the top stimulus on the top, what you'd say is that, well, half of it looks white, the other half looks about mid-gray. And he takes you out of the dome, and in fact, one side is painted jet black, the other is painted mid-gray. It's quite a striking phenomenon, right? And so this is what you're seeing over here on the right. Is there a laser pointer? Doesn't matter. If you look at the slide on the right, you'll see that basically what you're getting is a shift from the actual, which is going from mid-gray to black. The perceived goes from white to mid-gray. Thanks. That's what I was pointing at. Okay, so basically, one of the things that he claimed was that you need some kind of anchoring rule. And why he claimed you needed to have some kind of anchoring rule was because we don't experience relative magnitudes of lightness. We tend to have, if you ask me what color the shirt is, you say, it used to be black. No, it's been washed too many times, right? But you can make some estimate of its true reflectance. And that suggested that because the information, in principle, only contains relative information, you need to have something to anchor that onto the lightness scale. And he claimed that there was this anchoring rule. And he did these in contexts where there was usually the domes or mondrians, which are completely uniformly illuminated. Right? So there's no structure in the image that will allow you to identify what the change is or to estimate what the illumination is. And so what we did was to test this. Right? We did this in a bunch of ways. I'll just show you one experiment. This is actually coming out soon. But basically, we did this experiment years ago where what we did was we just started with this idea that in any achromatic world, that no matter what reflectances I used or what intensities I'd used, I'd always see the brightest thing as white. Seemed wrong to me, right? It just seemed implausible to me. So I said, well, what would be the case where it would be least likely to see that? Is a low contrast mondrian, a low contrast display that's very dim. So that's what we started with, and then we just multiplicatively treated this as if it was just an illumination change. We did this on a monitor. And basically the punchline is that the ambiguity in the input is also revealed in the output. Basically, what the visual system is doing is it's treating the highest luminance in a scene can vary from as low as mid-gray to here and grow all the way up to white here. But it scales as a function of the actual physical brightness. So we don't actually anchor lightness. Even though we experience at a particular moment, in a particular context, a fixed lightness scale, we don't necessarily have this arbitrary mapping onto a specific value. And so this is the more recent work that this is also just coming out. Is that we said, but maybe this is just about simple stimuli, right? The problem is that all the stuff so much of the work that's been done in lightness, apart from some of the stuff that Kazim has done, has been done on these displays where you basically are maximally ambiguous, right? So it's hardest to recover when I don't have any information about the illumination. How would I possibly know how could I tease apart the illumination from the reflectance? Well, some of the earlier work suggested that things like interreflections, the strength of shadows, can provide information about the intrinsic albedo of a surface. Another obvious candidate is specular reflections, right? So if I put some specular highlights in here, they provide some information about the strength of the contact of the surfaces involved. So maybe if we put patches in here of different lightnesses, we'd exhibit greater lightness constancy for these than we would for these. I know these just look like homogeneous things, but these are labeled matte and glossy because these are actually rendered surfaces. But because of the direction of the illumination field that we were using, they look exactly the same and they just look like a homogeneous gray. And here's what you end up getting, right? So this is a matte and glossy. The data look identical because the stimuli are identical, right? Each of these different colored dashed lines tells you what the true color is, right? This is the true reflectance of the color of the surround is that it's on background. So what we did is we mapped out the whole space. We looked at all combinations of the background, all combinations of target. And here's the interesting thing to note. You'll notice that the so-called simple displays over here, the simple center surround displays that people have studied for years, show this bizarre behavior where you get these big steps when you go from a decrement to an increment, which are missing over here. Right? And so, in fact, I think that this is where I disagree a little bit with Ted earlier this morning, is that these are so-called the complex displays, but these are actually exhibiting the much simpler behaviors. Right? So, in fact, this is the part I agree with them on, is because there's more information in here. So it looks, at least, if we look at the range of errors, if we take the range of errors to be some estimate of how good we are at estimating lightness, we can see that at least when we get to the glossy one, that the range is worse here, about the same here, but if I throw glossy in, it seems like I'm being better at getting lightness constancy out. That would be the diagonal, right? And to give you I don't know if you can see this, but it's a little bit hard to see. But if you look, if you can see, can anyone see the target in that? And you can see that this is the step that you can see. This looks quite dark. This looks quite light, right? But if you look at these are the same surface patches on the map thing below. And you see no such steps down here. Right? This is a much more well-behaved continuous transformation, but whereas here, this so-called simple display is actually exhibiting the most complex behavior. I also wanted to point, this is kind of a risk, but it works. After Ted's talk this morning, I scrambled into Photoshop to show that what he said is most color constancy illusions are not just changes in lightness. These are, in fact, the same colors. These are, in fact, the same colors, but you have a very strong change in the perceived hue. Right? So there are other interesting things here. That was a bit of a tangent, but I wanted to show it to you. So what we did was a bunch of control experiments. We did that first natural thing. Let's take all the same pixels, rearrange them as checkerboards. We're still seeing a little bit benefit of the glossy over its equated histogram background. So it still sounds like we're getting some kind of information. And so we did one more control experiment. We're finally saying, yes, if you have information about the illumination field, then in fact you do better at lightness constancy. Just to make sure, though, let's actually, instead of just doing this, because the spatial content of this is very different than this. This is white noise. This is something more like 1 over f noise. What if we phase scramble this? So the specular highlights are not going to look like specular highlights anymore. What happens? Well, now there's no difference. Right? So basically, this is where I got to the point where I really don't think that the visual system cares about extracting. It's just a lot of these phenomena are just simple processes of low-level mechanisms of most likely contrast normalization and the like. Right? So the punchline of that section is that we're good at accounting for image structure, but we're bad at getting the true lightness of the surface out. But I don't think that that's particularly important. Right? I think what's important is being able to get the structure out. What causes the change of what is responsible for the structure that's in the image. Right? And that's something we seem to be good at. And the last one that I'll work on to try to talk about, and this is the one that got me here, is gloss, right? So how is it that we can distinguish specular reflections from other sources of image structure? How do we know these are specular reflections? And just to beat this horse a bit, this is how I got here, right? So there's this very interesting paper by Modiyoshi et al. that was talked about this morning with the image statistics. And the basic observation was that there seemed to be, in the image, some diagnostic information that matte surfaces tend to have this negative skew, where the histograms of glossy surface tend to have this positive skew, right? And you can actually coerce the histogram of this into this, and you can actually see that it will transform it and make it look glossy. And it seems quite striking. It seems like this is actually what provides very strong evidence that the skew, or the luminous histogram, or something similar, such as subband skew, is used to compute gloss and lightness. And the problem I had with that is that basically the thing that I've been doing my entire life is that this is, again, just an entirely photometric cue. It's just counting pixels and looking without paying any attention to their geometric context, so the geometric structure in the image. And what the main insight was that it's these photogeometric constraints that are absolutely crucial in allowing us to distinguish different classes of changes and different classes of structure in the image. Right? And so if we start with something like this, which looks, I could show you all the data, but this is really the main thing. If I take the same highlights, but if I peel the highlights off and move them, right, I can force the histogram so that they always have the same skew. What you see is, quite compellingly, that these, except when these things are aligned in exactly the right place, these do not, in fact, look like specular reflections. Right? And again, this is basically, this notion of being in the right place is a photogeometric constraint. And that's the basic insight that I'm been pushing for in this, right? This was a histogram skew thing, which I already talked about. But this took a while to figure out, why does this work? Why if I take this image and I coerce it into the image, why does this look glossy? It seems like you're just doing something purely photometric, because all I'm doing is playing with the intensities of the pixels. But it turns out that if you look at where the brightest spots are in this image and I then force them to be brighter, they're always going to have the same geometric layout in this case and in this case. And this is exactly what would happen in the geometric constraints that are imposed by specular reflections, right? So this is the main insight. Now, so what is the information that allows us to distinguish different types of image structure? And this building on ideas from Zucker and more recently Roland and lots of other people, is this idea of orientation fields. There's got to be something in these shaded images. This is a picture from Jim Todd's paper, which is basically a rediscovery of Beck's old work on this. But you can see if you look at the orientation response in this color map, that these specular, so-called what were once specular highlights, do not blend in with the shading background. They create these huge orientation contrasts that don't exist in the cases where they're aligned appropriately in the glossy image. And so we have basically two photometric constraints that we're trying to talk about. One is orientation congruence, and that's data format we don't really need, and the other is position congruence. So most of the work that we had done, we didn't actually manage to dissociate whether it's just the orientation, so we created these 1D surfaces, and instead of changing their orientation, we also just, in addition to changing orientation, we could also just displace them, and hopefully you'll see that while this looks reasonably glossy, this looks odd and like pigment again. So we have another type of congruence that has to happen. Specular reflections have to be near the peaks in diffuse shading as well. So this comes out in this graph. But here's the important point. To return to this issue of scaling, right? And this issue of a constancy, this is exactly the same kind of failure that we saw in transparency. Recall that in the case of transparency, that if I just change the color of the piscator, or change the color of the transparent filter, it also changes its perceived opacity, right? That's physically wrong. The same exact thing happens with gloss, right? These three objects have, in fact, exactly the same physical specular reflectance, but they don't, in fact, generate the same percept at all. This image appears much glossier than this image, right? And it's because basically, we know why. We can tell by looking at it. Because we know why, because the contrast is much lower here of the specular reflections than it is over here. And the same thing happened in transparency, right? So it's the same issue with transparency. What the visual system is doing is it's using contrast, which is itself a local image structure measure, as the source of information by which it's gauging and scaling these other dimensions. And so it's not doing the scaling appropriately, but it's using what it has to use, what it has available, which is namely measures of local contrast of various kinds. What am I doing for time? I've got 2 minutes. So another part, which I'll talk a little bit at EPCV, is that how does the visual system scale different levels of surface gloss, right? Here's, again, I'm expecting inverse optics to fail. And I mean, if you just do a thought experiment, right? We know this, that gloss is one of the least constant things that may exist. And one of the examples I use all the time, I was going to show 2 pictures, but it doesn't, I can just tell you, is that if I spill a little bit of water on the stage, right, I have to find a place where I can get the specular reflection, a light source to hit that water to even see it, if it's just a small drop, right? You don't have anything like gloss constancy, right? So we're actually expecting this to fail. And one of the things that we got us into this was looking at a surprising interaction that people had shown before, is that just by changing shape, people got a change in the experience of gloss. So all of these surfaces actually have all the same physical gloss parameters, right? So basically what you're seeing here is that hopefully you'll see that they seem to vary quite dramatically in their degree of gloss, right? So the visual system, and this has to do with, so what we did was, this is a illumination from above, this is from the front, and for flat surfaces, you can see what happens here, right? If I move the light source so that it's projecting straight at the surface, I'm going to get a surface that's largely covered by specular reflections. If it's above, for such small relief, it's only going to be the very top little bits of these bumps that are going to generate any image structure that's due to specular reflections. And so what we ended up doing was basically saying, going back into the literature, saying, look, we're not getting the physics right. We're just using 4 different cues, or 3 different cues to what that we use as surrogates to estimate gloss, which is namely, if we start with something which is high gloss, we can talk about the coverage of the surface. That is, how much of the surface appears to be covered in specular reflections, the contrast of those reflections, right? Whether it's a big contrast or a small contrast, like down here, right? So this is low coverage, this is high coverage, only little portions of the specular reflections, and the sharpness of those reflections. We didn't make this up, this is in the literature, right? And what we ended up doing was showing that we could, in fact, account for people's gloss judgments just by the simple additive model of these different cues, right? Again, you're not doing the inverse physics on the scaling problem, but you still are just using the properties in the image that you're attributing to specular structure as the source of information that you're using to do this scaling, right? So to finish up, I won't get to go through all this because I see I'm in the yellow. Summary. So hopefully I've tried to convince you, or at least provoke you into thinking about that the presumed intractability of inverse optics results from construing the problem of vision as a series of recovery or estimation scene variables. I don't think that's the right way to think about vision. I think what we should be spending our time trying to do is trying to understand what it is. First, what are the distinctions? What are the things that we can discriminate reliably? And what's the informational basis for that discrimination? A lot of this is repetitive, and I'm out of time, so if you want to read it, I will leave it to you, and thank you.
Okay, so questions?
Roland, how surprising. An opinion, perhaps.
I gotta say something after every talk. So, does that mean that you don't think that absolute physical quantities are ever an important thing? Because I mean, so for example, I mean there are material consequences if you misestimate the weight of an object that you're trying to pick up or something like that. There it seems like, yes, there is a disambiguation issue, how much of the sensory data is coming from the properties of your own body and how much is it coming from the weight, but the absolute value is also something that is really relevant.
Yes, it can be. And I think that, but basically I think that the ones that are, we can actually, there's some notion of what the consequence of certain scalings is, right? So, or are, right? So what it's not that I think that they're never relevant. There's certain things, for example, which I didn't talk about, certain shape estimations. In order for me to grasp this, I have to have a reasonably reliable sense of what that shape is. But there are other dimensions, like color. I don't even know what it means to scale distance in color, right? I mean, there's a big issue in color space, whether or not vector length means anything. And it's not clear that it does or what it could mean if it did, right? So I think that there's certain class of distinctions in shape, size, but these are usually descriptions of the world that I think are critically action for motor behavior, right, for action, right? So, and usually have to be scaled in body coordinates anyway. So how much force is it going to take for me to jump off there or to step down from here? Certainly knowing that things are, but I still, so take gloss, right? There are consequences if I get the gloss wrong, right? Maybe it's, I misjudged how slippery something could be. But I still have yet to see, it doesn't mean, I don't know what it means to get it right. What's the scale that would actually provide the most fit, the greatest fitness for an animal, right? I think if we could somehow bridge that answer, so if we could say, okay, we might actually want to have, like for pain, we might want to have this accelerating nonlinearity because, you know, a little bit's okay, a little bit more is getting kind of bad, but get the hell out of there, right? Stop that, right? And so there's certain cases where the scalings will make a lot of adaptive sense, but other times I think it's just about, mostly like lightness, I think a lot of it through these normalization things is a coding issue. You just want to be able to tell the differences between things. So lots of things are logarithmic, so it's just a percent change, right? And it's probably based to do some kind of multiplicative gain control type of process, right? But that's just so you can still code for differences, right? Not that you care about the size of the differences as much. That's my working hypothesis.
Okay, so first, as for the ambiguity issues, I remember that you are originally the Gibsonian, so that it's quite reasonable that you starting with that assumption. But the question is that, of course, you know, only we can get information is something we can eventually obtain by moving our head or doing something. But under some situation, we can move our head and something. And that kind of situation, the Bayesian estimation, a sort of ambiguity solution.
Right, but the Bayesian, the thing is, in those cases, what I'm basically saying is that you have to have a way of obtaining that information. Right, so you have to have a way that there has to be a learning process by which you can extract it, and by like I think the machine learning idea of TED is close in terms of my own views. I think it is a classic learning and evolution. We are basically trying to recapitulate evolution, right? And I think that we're just trying to figure out what is a set of signals that could be used, and a lot of these things, the input, I think, like everything else in biology, the input is not the image. The input is the entire history, right? It's the input conditioned by the entire evolutionary and learning history of an animal, right? And so it's more that there are certainly the cases, that's why I think some cues are still so effective, because in the unambiguous cases, you learn how they're correlated and tied to depth, how certain cues are associated with depth, how surface normals point at light surfaces, light sources, right? So all those things, if you have that information, you can build in those correlations, which you can then build up a set of priors, right? And you can see how they depend on the changes in viewpoint and develop some of the likelihood information. So I'm not anti-Bayesian in a sense. I do think that in the cases where it's ambiguous, because we can construct them, that you've got to be using some kind of prior information, right? But I don't want it to be magic that gives me that prior, gets it in my head. Right? I think without some notion of specificity, then it's magic.
Okay, so another thing is that the word term inverse optics is quite controversial, I think. But for me, optics means that there's some physical process actually generate image. And inverse optics means that somehow it has to return.
Yes.
But what you are saying is that we don't recover everything. We just recover something relevant to our life. So it's already not inverse optics.
Well, I think that there's another way to put this, right? You can think of this in a formal way. Is that the world is, you can think of as a set of equivalence classes. There's a set of things that we can discriminate, right? So if we think about our set of discriminations as being able to parse the world into different equivalence classes, then we can just ask, what are those sets, right? So to me, that's the game of, if you want to call it inverse optics, what most people mean by inverse optics, I think, is something like inverse graphics, right? And I think that's so opposed. I probably, to be fair, I mean, I set up the title a little bit to be controversial, but I think I'm one of the few people that's not in computer vision who believes in intrinsic images, because I experience them, right? I can tell the shadows and shape, and I think that we do recover those. And so I think that that's still where I want to put my money, because I do seem to be aware of what, that's an illumination change along that wall up there, right? I can tell that. Now, if I make a lightness judgment, if I'm forced to, I'll tell you it's all the same color, right? Because I know it's all the same color, but if you actually made me match it, that shadow part I'm going to match to be much darker, right? Or at least somewhat darker. Right? And I'll show a partial concept.
So essentially, you're being very old-fashioned.
In a sense.
You're going back to where people used to believe in heuristics, and they were mostly geometrical, and they were mostly associative, and that's what people would use.
Well, I think that you want to go more?
Well, but I would also say that just like you're critical of other people's papers, you might want to be critical of thinking that, yes, you can always tell shadows from or illumination.
No, I
because it's very easy to get fooled there, too.
No, I think that's exactly right. But I'm saying that in those cases, I would expect that whatever the information is that we have historically come to use to rely on it isn't available, right? So we should be able to be predictive of one of the cases where we can fool people. Right? The game doesn't change. The game is to figure out what that information is that allows us to do the things that when we can discriminate it, right? I think that we're better at doing these classification things, but we're not perfect at it either, right? We make them, and when we do make them, they're quite striking when you finally get it right, right?
That's why they call heuristics or rules of thumb, because you can go wrong applying them.
Or they're based on on certain classes of information, right? To get back to the Gibsonian point, I think that there is a bit of returning to that, and I don't think Gibson most people don't view him as old-fashioned, they just think of him as wrong, right? But I think that,
yes, they're right.
But I think that in a certain sense, he just went too far. He was trying to claim that there is sufficient information in the input to uniquely specify its source. And what I'm saying is soften that a bit. There's sufficient information to explain the class of things that we can discriminate. right? It's a softer claim, right? I'm not making a naive realism claim. I don't know if that satisfies you or not, but you have 30 seconds to give me more shit.
I think the time is
I had 20 seconds.
20 seconds and a very quick short questions. Oh.
So I do computer vision, so this might be a completely off question, but do you think the fact that you cannot recover quantitatively the scaling is fundamentally related to the fact that the eye's dynamic range is somewhat relative and not absolute?
Yeah, I actually think that's what I meant by gain control. I think a lot of these things is that, we have this visual system that can operate over an incredible range of intensities, incredible range of contrast. And the main thing you want to be able to do, a lot of these quantitative things, is to just make sure that you can encode structure in the image, right? In order to do that, you have to change your dynamic range of sensitivities in a way that's dictated by the input, right? So I think it's actually a very good question. That's basically what I do believe, yeah.
Thank you very much.